Hi, welcome to my video essay / virtual class type situation. Today we're going to be talking about data inference, why it's important, how to do it. I'm going to hit you with a quote, and hopefully everyone listening should know what this quote is from, but definitely all the English majors in the room. Romeo, Romeo. Hopefully everyone just said, "Wherefore art thou Romeo?" Now, what you just made was an inference. Based on the information given, Romeo, Romeo, you filled in what you thought was the most logical next possibility. Wherefore art thou Romeo? It's a very famous quote. A lot of people should know it. Hopefully, everyone should know it, but I'm not going to assume everyone's read Shakespeare. He's wrong for me. So, this type of inference is essential for what we're going to be doing today, because in data inference, it's impossible to ask every single person their opinion on a subject. It's impossible to pull every single data point in order to get to a logical answer. Yet in life, we are still going to have to reach that conclusion. We're still going to have to jump to conclusions, even without every single possibility mapped out. And today, we're going to talk about how to do that with a set of data. So data inference is very important. It's applicable to all sorts of things we use in our everyday life, such as polling, medicine, marketing, science, social science, everything, everything. Some examples in when you're going to be using it is, let's say you have a fixed collection of data, but you only know a sample of it. Let's say some fact is unknown. You're going to have to use statistical inference to deduce an answer. Or let's say there's an event that may or may not happen. We're going to use a sample pool to determine the likelihood of said event occurring. And now, I hope you realize that by describing those three things, I covered almost every decision and situation you're going to be in life. So pay very close attention, because you're going to realize that statistical inference and data inference is so important. It's so important. And I'm going to use some daunting words, but I promise it's very manageable. So let's talk about hypothesis testing. This is going to be the most important aspect of data inference. So in order to answer or find a solution to something, you're going to need to ask a question. So the question I'm going to be using a lot today is, do we need to improve McConnell lunch? I don't think we do. I love McConnell lunch. But let's say I wanted to poll the general population. This would be a question super applicable, something we ask a lot. A lot of people have discourse on it. So how would we go about doing it? We're going to do something called hypothesis testing. So you're going to compare two opposing statements and then use data samples to determine which is more likely to be correct. So the two different questions or opposing statements are going to be the null hypothesis and the alternate hypothesis. So really quick, I'm going to write on the board for you behind me. The null hypothesis is going to be written with H0 in subscript, and then the alternate hypothesis is going to be H subscript 1. Just for later on, I'm going to start simple. I don't want to write it all out on the board, null hypothesis, alternate hypothesis, so just so you have it. Now, the null hypothesis is the claim that the effect that we are studying with our hypothesis doesn't exist. It's basically the antithesis of what we're studying. It's that this thing we thought was going to happen didn't happen, the null hypothesis. The alternate hypothesis is the opposite of the null hypothesis and suggests the opposite of the effect we're studying. So these two have to be opposites of each other, and in your experiment and your data testing, you're going to find which one is true. So level of significance is represented by this Greek letter. It really looks like a lowercase a, but I'm going to be simplifying down level of significance to that symbol. The level of significance represents the range of accuracy in which we will accept or reject the null hypothesis. 100% accuracy is impossible. Nothing's ever 100% accurate. Even remember when we did the coin flip experiment, where we know 50% of the time it'll be heads or tails. But then when we actually did it, we realized, it's not a clear 50%. So that our hypothesis 50% of the time you'll flip heads or tails isn't 100% accurate. So you have to select a level of significance. And that typically will range between 0.5 or 5%, meaning you'd have 95% accuracy in order to confirm your hypothesis. And when you're flipping a coin, 95% of the time, yes, you get that statistic. Okay, p-value states the likelihood of seeing your result if the null hypothesis is true. Now, the p-value has a formula to find it. The p-value is going to be z equals x minus fancy Greek letter over another fancy Greek letter, where equals mean x equals your recorded value. And that is the standard deviation. Again, just for when we're getting all of this together, I want you to have all the information you need. So the formula is right there. And so the p-value, again, states the likelihood of seeing if your result, seeing your results and seeing if the null hypothesis is true. If the p-value is less than the chosen level of significance, you would have to reject the null hypothesis. So another important term, test statistic. This number states whether or not your test results are going to be significant, and it's determined from the sample data collected. There's also critical value. This is the threshold that determines if your test statistic is enough to reject the null hypothesis. And then there's also degrees of freedom, which helps determine how much data can vary. Now, once you have to go, now you have all the vocab terms you need. Let's get into the steps of actually doing it. So there's two types of hypothesis testing. There's a one-tailed test and there's a two-tailed test. So a one-tailed test, you would expect a change of degree in only one direction, an increase or decrease. And it's not going to be in both directions. So basically, if we were testing to see if people wanted to change McConnell lunch, we'd only be looking to see if enjoyment went up or down. We wouldn't be looking at anything else. This test looks at just one side of the data, and if the data falls in the critical region, as determined by your critical value, then you're able to reject the null hypothesis. And your goal of a successful experiment is to be able to reject the null hypothesis. Okay, the other type there's two types of two-tailed testing. So there's two types of one-tailed testing. There's left-sided and there's right-sided. So on the left side, if the alternate hypothesis says that the true parameter value is less than the null hypothesis, then it's a left-tailed test. But on the right side, when the alternative hypothesis says that the true parameter is value is greater than the null hypothesis, then it's going to be called a right-tailed test. That's not super important, but just so you have all the tools you need for this. Okay, the other type of test is the two-tailed test. And this is used to check for significant change or difference in both directions, aka if it's greater or less than a specific value. You'd use this if you didn't have a specific expectation for how the data would change. And there's a formula for it. It's not super important. Mostly it's knowing which type of test you want to run, if you have an expected change or if you don't. So there's also, obviously, people are going to make mistakes in this. That's super normal. That's super okay. So there's type 1 and type 2 errors when finding a conclusion. So the type 1 error entails you rejected the null hypothesis, but it was in fact true. And this is denoted by, again, that Greek letter symbol. And then there's a type 2 error, which is we accepted the null hypothesis, but it ended up being false. And this is a new Greek letter. Totally okay. It's okay to make mistakes in your experiment, and just means you might have to do it again, but it happens enough to everybody that there's a specific term for messing it up, and I just thought that might make everybody feel better. All right, so let's talk some visuals now. Let's go through the steps of running the experiment, testing it out, using your data, gathering your data. So, step 1, you're going to define your null hypothesis as well as your alternate hypothesis. Okay. Step 2, you're going to choose a significance level. I hope you remember what a significance level is from before. If not, go ahead and consult the notes from earlier. All right, step 3 is going to be collect and analyze data. Okay, and then step 4, perfect. Now, once you calculate this test statistic, you're going to reach a place where you're going to need to make a decision. And then your decision can be one of two things. You can reject your hypothesis, or approve it. Now, some notes about that visual outline of the steps in the process. When you're choosing the significance value, you are going to have to calculate your p-value there. And remember, the formula was z equals x minus the mean all over the standard deviation. Also note, when you test the statistics, you would have to choose between 3 types of tests: a z-test, a chi-square, and a t-test. But since we're just trying to understand the process in pretty broad terms right now, I'm not going to make us delve into those tests, but just know that's an opportunity outside of this video, outside of this class period, to learn if you just are interested in a little bit more extra fun. Now, when you're done testing the statistics, you have to compare the results to either the critical or p-value to determine whether or not to reject the null hypothesis. If you're going to compare it to the p-value, if the p-value is less than or equal to the significance level, then you'd reject the null hypothesis. If the p-value is greater than the significance level, then you fail to reject the null hypothesis and the experiment doesn't work the way you thought it would. If you're going to use the critical value as a comparison, you'd refer to the statistical distribution table to find the critical value based on the chosen level of significance. If the test statistic is larger than the critical value, you would reject the null hypothesis. But if the test statistic is smaller than or equal to the critical value, you would fail to reject the null hypothesis. Now, let's talk about margin of error and presenting your results, because you've done all this work, you've done this wonderful experiment trying to figure out, do people want a new lunch at McConnell, this and that. You have to now share it with the general population who maybe haven't had a presentation explaining how to understand all of this. So I'm going to change up our analogy just to keep it a little bit exciting. Let's say Georgia French, our beloved Georgia French, is running for the next president of Scripps College. We take a poll, we poll the general population, poll baby poll, and we get results that say, we do all of this math, and we find that the polls show that Georgia French will receive 46% of the vote with a plus or minus 3% margin of error. It's awesome. We did a whole ton of work with all of that. We found the p-value, we found significance level, we did all of that. What does this sentence mean? How are we going to present our results now? So the 3% indicates that the sample size was sufficiently large and the actual percentage of Georgia voters are likely to be within the range of 43 to 49, because we said 46% of voters are likely to vote for her with a plus or minus 3% margin of error. So you add 3 or you subtract 3 to that 46% to find sort of the range of what we found. Because everyone makes mistakes. We have formulas for calculating our own mistakes. That's great. We all do it. It's really comforting. So how to pick a large enough sample size for doing all of this? Does the size have to get bigger as the pool gets bigger? Let's talk about my favorite analogy of chicken soup. Let's say we have a cup of soup and a bowl of soup. We salted enough, and we salted both of them equally, and we want to figure out if the pots have enough. So we stir, take a spoonful from the small pot. Am I going to go get a whole new spoon, clean it, get a bigger one, try it? I have 2 spoons to clean. No. Because this one spoon, we trust this one spoon to be large enough to represent the entire pot of soup. And it works the same with stats. So the sample size is more important than the sample's percentage of the overall population. In order to get a meaningful result, the sample size just needs to be large enough to reflect the variability of population. It doesn't need to contain a certain percentage of the population. And this is seen in the margin of error formula, which is 1 divided by square root of n being the sample size. Notice there's no total population size in this calculation. So we have all of our formulas. We found why is data inference important, how to do data inference, how to set up our own experiment, how to present our findings to the public. I hope you enjoyed this. I hope you learned some things, and it was a pleasure. Thank you.